Hi there, welcome back. This is lesson 3 in our unit 13 unit, nuclear chem. Today we're going to talk about the difference between nuclear fission and nuclear fusion. Joining us today is special guest Miss Vampus.
Hi everyone, hope everyone is doing well. So like Miss Scanlon said, we're going to focus on nuclear fission and fusion today. Before we begin, Miss Scanlon, do we have any announcements to make?
A few announcements. One, the best way to go about this lesson is to take out the note sheet that says nuclear fission and fusion and follow along. And then for homework, Castle Learning number 27, fission and fusion, is due tonight by midnight. And just make sure that you are following the calendar for any other announcements your teacher may give you.
Okay, great. So let's jump ahead. Okay, so here we have on our first slide types of nuclear reactions. So we already, in our previous lessons, talked about natural transmutation. And here are the types: alpha, beta, positron decay, fusion. Okay, and now we're going to also look at artificial transmutation as well, which is fission and fusion.
So one thing to point out, anything that is natural, it kind of happens on its own. And things with artificial, it's man-made, meaning it doesn't happen, something needs to get that started. So again, like Ms. Vampus had said, the natural transmutation, and again, that's changing one element into another. The alpha beta positron decay. Yesterday and the day before, we worked on writing those decay equations. Today we are talking about fission and fusion. And so fusion, that's how the sun makes its energy, and that's natural, it happens on its own. And then going into like the atomic bomb, that doesn't magically just spontaneously happen. Somebody needs to make it and set it off.
Right. So like we said, it's artificial. Okay, so something needs to set it off, like Ms. Scanlon said. It's man-made. So are we on the third page now?
Yes, we are.
Third slide. Awesome. So the word we want you to focus on here, fission. Think of splitting into two, okay? Splitting. Something large splitting into something smaller. So in this case, fission is splitting of heavy elements, which have large nuclei. Heavy element plus neutron yields two middle-weighted nuclei plus one or more neutrons plus energy. So we're going to explain to you what that actually means.
So right here we have an isotope of uranium. So this isotope right now is stable. And so in order to get this to be broken down, a neutron is kind of thrown at that uranium atom. So when these two things collide, it breaks down that uranium into barium and krypton. So big uranium is broken down into two smaller elements. And then these represent your neutrons. So if you think about it, let me just change colors here. This top number up there, that's your atomic mass. So that's how much the atom weighs. So uranium is 235 atomic mass units. And then when it breaks down, these two smaller elements, they have much smaller masses.
Right.
One thing we also kind of want to have you think of when we're talking about fission, even think back to living environment when you talked about binary fission, where you had one cell that broke down into two smaller cells. So in terms of chem, instead of cells, you just take one element and then it breaks down into two smaller elements.
That's right.
So here's a GIF that kind of shows what's going on.
Oh wait, Ms. Scanlon.
Yes.
Do we want to talk about how the atomic mass is conserved?
It's a good point. It's a good point to go back to.
Yeah.
So backtracking a second, let me just clear this up. If you notice here, and this is again stuff we covered writing decay equations yesterday and the day before, if we're adding up the total mass of the left side of the equation, we have 235 plus 1. So on total, the left side has a mass of 236. So if you were to add up 142 plus 91 plus if you have 3 neutrons, that's 3. Add them up all together, you get 236. So remember, mass is conserved. You can't just magically get rid of stuff. It just takes its form in different elements. Same thing with the atomic number. So remember, atomic number is the number of protons an element has, and it's specific to each one. So if you add up the left side, you get 92. And same thing if you add up 56 plus 36 plus 0, you still get 92.
That's right. Okay, so now that we've explained that, let's go ahead and watch this little animation for us to visualize.
So here you had that uranium atom, and a neutron hit it, and then you see it broke down into the 2 different elements, the krypton and the barium, and also let out those 3 different neutrons. Okay. Jumping forward is fusion, and this is when you have smaller or lighter elements coming together to form one heavier one. So this is what happens in the sun, and this is where all like the solar energy comes from. You have these tiny little hydrogen atoms. They come together to form, this is now a heavier hydrogen atom. Remember, it's an isotope because the mass changed, but since that bottom number stayed the same, it's still hydrogen. And now when you have a light and a heavy hydrogen coming together, you're forming helium. So again, it's these smaller things coming together. That's what fusion means. If you think about like an Asian fusion restaurant, to come up with something off the top of my head, it's different kind of cultures and foods coming together in one restaurant.
That's right. So now we're going to take a look at the animation to visualize this.
So we had 2 different isotopes of hydrogen coming together. So H3 and H2, those are different forms of hydrogen. When they come together, they fuse, and you left with a helium atom and some energy.
Right.
So,
all right, so in our next slide, we're going to compare and contrast fission and fusion. Okay, so like we stated before, in fission, the nucleus splits. In fusion, nuclei unite, and it gives much more energy than fission. Let's take a look at the middle. What do they share?
So both reactions are producing a lot of energy, and then nuclear reactions kind of break some of the rules we've talked about before, and so mass is now converted into energy. So these bullets are happening by both reactions. One thing to kind of think about, and I'm starting it right here, a fusion reaction gives off much more energy than a fission reaction. If you think back to a while ago, when we talked about bonds forming and breaking, we looked at barf. So if you break a bond, energy is absorbed. If you form a bond, energy is released. So if you think about it, we're not really talking about bonds. With fusion, you have new elements forming and coming together, and it's releasing so much more energy. So that bullet point right there is a huge part of what fusion is.
Okay, great. So in our next slide, we're going to talk about radioisotopes and the benefits and risks.
So we're going to spend time tomorrow and the following day talking about these in more detail, and we kind of mentioned this a little bit. But these radioisotopes, these radioactive isotopes, that means they're unstable, and so they will naturally decay into other things. So you might think radioactive, oh my god, it's like poison. Some of them are pretty beneficial. So some of them can be used as tracers. There's a lot of medical benefits of them. They're used to diagnose different diseases and different treatments. Foods can be stored longer. It's used for nuclear power. You can also do, and we'll talk more about this tomorrow, radioactive dating, to figuring out how old stuff is. And then these 3 elements right here. So first, the uranium and the lead, they have something called really long half-lives, and we'll talk more about that, what that means tomorrow. but they're generally used in geological dating, whereas C14 is used for kind of dating living material. Again, that's more stuff we'll cover tomorrow.
Right.
Now, some of these, there are risks with this, because for obvious reasons. So one of the things is they can do biological damage, and this is kind of what most people think about when they think about nuclear and radioactive stuff. They have very long-term storage, so things with very, very long half-lives, again, the topic for tomorrow, they take forever to decompose, way more than your lifetime, so you really have to think about how these things are stored. Accidents happen. If you think about Chernobyl, that happened, I think, in the 90s. There's also an HBO show last year. It was pretty good. The whole nuclear power plant kind of exploded, and that was not good. And I'm pretty sure it happened in Japan in like the mid-2000s. And then you produce all of this nuclear waste. So for everything, there are these benefits, but there are also a lot of risks.
That's right. Okay, guys, so that covers it for the notes section. We're going to do a couple of practice Regents questions. So let's take a look at the first one. But before we do that, Ms. Caitlin, do you have anything to add?
Nothing to add, but just since we're jumping into the question portion, it makes sense if you kind of pause the video and try these on your own and then come back to hear our explanations of them.
Right. So we'll just read through the first question together. In a fusion reaction, reacting nuclei must collide. Collisions between two nuclei are difficult to achieve because the nuclei are A, both negatively charged and repel each other, B, both positively charged and repel each other, C, oppositely charged and attract each other, or D, oppositely charged and repel each other. Take a moment to answer this.
If we think about this, let me start over. In an atom, so I'm drawing those positive things are your protons. Those things with zeros are your neutral neutrons. And then you have these electrons kind of floating. So remember, that center part is your nucleus. And in your nucleus, you have your protons and you have your neutrons. So protons are positive, neutrons are neutral. So the overall charge of a nucleus is positive. Okay? So if we're looking at trying to collide two of these different nucleuses, or nuclei I should say rather, they're both positive. So we can get rid of choice A, and we can also get rid of C and D. But if we're thinking about that, things that are positive, so if you have two magnets that are both using the same side, things that are the same repel each other. They don't want to be near each other. So getting these positive things to come together is very, very difficult.
That's right. So the answer then would be
B, both positively charged and repel each other.
Okay, great. Now if you have if you want to review that, this would be a good time to pause and do the question again, or rewind a little bit. We're going to go ahead and move on to question number 2.
Okay.
Given the fusion reaction, look at the formula, plus energy, which particle is represented by X?
So this is something we had talked about before. So remember, the top numbers, and this is something we did yesterday and the day before, the top number is on the left side, 2 plus 2 equals 4. So that means the top number of X needs to be 4. And if you add up the bottom numbers on the left side, 1 plus 1 is 2. And so the bottom number of X has to be 2. So with that, we can get rid of A, C, B, and D. One of the important things to point out though, this bottom number, remember, is your atomic number, okay? And that's the number of protons, and it's also the element ID number. So remember, not every element has a very specific atomic number. No two elements have the same atomic number. So this number tells you on your periodic table what element it is. Okay. Moving forward, number 3.
Okay, so number 3 reads, which change takes place in a nuclear fusion reaction? A, matter is converted to energy. B, energy is converted to matter. C, ionic bonds are converted to covalent bonds. D, covalent bonds are converted to ionic bonds.
Okay, so right off the bat, we can get rid of answer choice C and D. When we're talking about nuclear chemistry, we're not talking about these standard chemical bonds. So ionic and covalent bonds will not be mentioned at all in this unit. So when we're talking about nuclear fusion, as Ms. Vampus was reading the question, I wrote down here kind of a summary of what these two reactions are. Remember, fusion is two small things coming together to form a large one. And fission is a large one breaking down into a small one. So that we're focusing on the fusion aspect of it. And then if we think back to the Venn diagram slide, all these nuclear reactions, doesn't matter if it's fusion or fission, it takes that matter and converts it to energy, making it answer choice A.
Nice. Okay, let's move ahead to practice question number 4. Nuclear fusion differs from nuclear fission because nuclear fusion reactions A, form heavier isotopes from lighter isotopes. B, form lighter isotopes from heavier isotopes. C, convert mass to energy. D, convert energy to mass.
Okay. So again, we have fusion is two small things coming together to form a large one, and fission is a large thing coming together to form two small things. So it's asking us about nuclear fusion, and that's taking small things and making a big thing. So forming a heavier isotope from lighter ones, answer choice A is that one. It is worded a little bit weird, but if you know fusion is small plus small equals big, then you can kind of say, okay, big is formed from two small things, and that's what A says.
Awesome. All right, moving on to Regents number 5 practice question. A nuclear fission reaction and a nuclear fusion reaction are similar because both reactions A form heavy nuclei.
You can read the answer choices yourself, children. Okay.
Yes, read it
yourself. Okay, so this is kind of going back to the Venn diagram slide. What things do they have in common? And both of them release a large amount of energy.
Energy.
Yay! Okay.
Yes.
And even if you think about that, nuclear reactions, you're using it for nuclear energy. You can power cities with nuclear energy. So the energy needs to be released so we can use it as humans. Okay. Number 6, it says, in which process is mass converted to energy by the process of fission? So, fission, again, we are breaking one element apart and turning it into smaller ones. And also, we want to make sure the mass is conserved. So, the best thing right now, the answer, is B. And the reason is this. So when you're working with a fission reaction, you have a heavy element, and you're forming two smaller elements, and then some kind of part of it. Now, D is very obviously fusion. Now, you might be looking at A and C. So if we look at C, you make the argument that it is breaking up. The element is breaking up, but that is just a nuclear decay question. And if you even look at it, these numbers aren't balanced.
Okay? No, they're not. Mm-hmm.
So that can't work. And then A just kind of shows the conversion back and forth between nitrogen and carbon, and that's not breaking up into two different elements. Okay. Last one for today, number 7. says which statement explains why nuclear waste materials may pose a problem. And so that was the last content slide we talked about, and in the risk column. And one of the problems with nuclear things is that answer choice D, they frequently have very long half-lives and remain radioactive for an extended period of time. So again, if you're not quite sure what a half-life is, that's okay. That is what we're covering tomorrow, and you'll kind of understand the reasoning more behind why we chose this answer choice. So on that note, this is it for this lesson. Hope this was informative. Just make sure you do finish the CalCit learning that is due tonight, and have a wonderful day.
Have a good day, guys. Take care.
Bye.